Hi, my name is Ekta Raj and this is Physics 2212 Lab 5 Magnetic Braking with Faraday. In this lab report, I will be going over introduction, key ideas and formula, procedure, computational model and conclusion. The goal of this lab report is to collect observational data of a magnet falling through a conductive tube of aluminium foil that we were provided in the lab, and then model that magnet falling through the aluminium foil in the WebB Python, and then compare the computational model with the observed data. You can see the findings on the screen. The key ideas and formulas used in this are Faraday's law, and you can see the formulas on the screen. The first one I used is the one that relates the integral of the dot product between the induced electric field and the length of the outer edge of a closed area to the negative derivative of the magnetic flux, which is curly integral of E dot dl, which is minus d phi b by dt, which is like the magnetic flux, and then where the magnetic flux is equal to the dot product between the magnetic field and the area where the magnetic field flows through. Another set of key ideas and formulas are as follows: a magnetic force on a wire loop, and when considering the magnetic force on a loop, the following equation is derived, which you can see on the screen, and the Newton's third law, which says that the magnitude of magnetic force on the loop is equal to the magnitude of the force on the magnet by the loop and opposite interaction. And we have also used Ohm's law and its relation to the Faraday's law here, which is I is equals to voltage divided by resistance, and voltage is equals to which is EMF, which is minus d phi by dt, which is the magnetic flux. Here you can see the visual model of the experiment that we did in the lab. So the system is a falling magnet and the surroundings is the aluminium foil tube and earth, and the F1 is the magnetic force on the loop, and F2 is the force on magnet by the loop due to the Newton's third law that we discussed previously. And in this I have assumed that the only forces acting on the magnet are the force of the gravity and the force from the loop. You can see the procedure for the lab report on the screen. Now let's go over the observational results that I got. You can see the table on the screen, and I will talk about the time between the magnet first entering the aluminium foil tube and when the magnet leaves the tube, and the average time interval for this was 0.724 seconds, and I considered the length of the tube to be 0.46 meter, width in a radius, total radius, magnetic dipole, and mass of the magnet can be seen on the screen. You can see the code I wrote on the screen that helped me with the calculations. This is the code I wrote to calculate the magnetic field and magnetic flux. You can see the remaining of the glow script code on the screen. Based on the results I got from the glow script calculation, you can see the computational results in the form of the graph, and you can see the values below each of the graph. Now I will go over the conclusion. So when the magnetic dipole moment found in the lab was used, the simulation predicted that the magnet would take 0.435 seconds to pass through the tube. This value does not match the observed value which we saw in the lab. When the magnetic dipole moment is increased to 2.166 ampere meter square, the simulation predicted that the magnet would take 0.724 seconds to pass through the tube, which is identical time to the observed average. Results suggest that the magnetic dipole moment found in lab 3 may be inaccurate, and that 2.166 ampere meter square may be a more accurate value for the magnetic dipole moment. Possible sources of error for this are the air resistance, measurement error used meter stick to measure tube, and timing error when determining the magnet enters and exits the tube. Now I will go over the first what if question, which is what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So resistivity is directly proportional to the resistance, so nearly zero resistivity equals nearly zero resistance. Nearly zero resistance will lead to a large induced current I according to the Ohm's law, as current is inversely proportional to the resistance. And we know that the current is related to magnetic force by the equation shown below, and a large current would mean a large magnetic force. And thus by Newton's third law, force on the magnet by the loop would be large, and the net result would be the magnet would fall with lesser speed because the force on the magnet from the loop would be much closer in magnitude to the gravitational force. Now I will answer the second what if question, is what if holes or slots were cut into the tube? How would this affect the ring currents in the model? They would disrupt the continuation of the rings in the aluminium tube, and the rings would allow for induced current to flow around the tube as the magnet falls. Disrupting these rings would reduce the induced current, and the induced current is related to the magnetic force, and as a result, the magnetic force by the loop decreases, and the force on the magnet by the loop decreases. And the net result will be the magnet falls with greater speed and taking less time because the magnitude of the force of the magnet is much less than the force of the gravity.